Well, thanks to everybody on the Zoom conference tonight. All the people on the live stream over on YouTube channel, and of course the people that signed up and RSVP'd on Meetup. Thank you. Thanks for joining us. Quick introduction here with our speaker. We're so lucky. Again, Franco has been doing a bang-up job on finding just these great speakers all over the world, and that continues tonight as we introduce Jani Radebaugh, who is an American planetary scientist and professor of geology at Brigham Young University, and she specializes in the field studies of planets. And her research focuses on, obviously, Saturn's moon Titan, but also Jupiter's moon Io, our own moon, Mars, and Pluto too. She is a science team member of the Dragonfly Spacecraft mission to Titan, the IVO Io mission proposal, and the Mars Median project. And hopefully we can hear a little bit about those tonight. She was also an associate team member of the Cassini-Huygens RADAR instrument from 2008 to 2017, and a graduate student scientist for Io on the Galileo mission. Well, back in December of 2012, she and her colleagues on the Cassini mission announced the discovery of Vid Flumina, which is a liquid methane river on Titan. It's over 200 miles long and looks an awfully bunch like the Nile River. Well, Dr. Radebaugh has appeared as an expert contributor on lots and lots of TV programs, including the Science Discovery series, How the Universe Works, The Planets and Beyond, as well as others on BBC and Nova. And it is our pleasure tonight to welcome to our screens, the small screens, the TV screens, and into our houses, Dr. Jani Radebaugh. Welcome, Doctor.
Thank you. I'm so excited to be here. Thank you. I'm so impressed to have seen all the images taken by your community. I think the amateur community does such great work. And actually what I do is go straight to Twitter and look for those amateur space photographers and even sort of amateur planetary image processors the minute something fun happens, like the DART impact, because NASA's busy doing what they have to do and the scientists are busy doing the calculations, but the amateurs can go grab the images and process them and get a good product out quickly. And so there's a great role to fill by everybody doing what you're doing right now. Beautiful pictures. I'm excited to be here and to talk to you a little bit today about the Dragonfly mission. And you can see on this picture right here, there's a team picture down here at the bottom. This is a little bit pre-COVID. We're going to meet again, it turns out, next month for the first time in person since COVID. So, well, actually, I think they did meet a few of them last year, but we're starting to sort of regather together. And this team has grown quite a bit since then, especially in engineers. But we're pretty big. Notice us, we've got a lot of people. I'm one of about maybe 50 team members, and I will try to talk to you a little bit today about this mission, what it is, and how exciting it is. First thing I want to do, though, is just a quick tribute or just acknowledge that this has happened. Jim McDivitt, I think, just in the last day or so passed away, and I'm so thrilled and grateful for these pioneers of space and space exploration for leading the way and getting footprints out there in the solar system. And I was privileged to be able to meet him once too. So it's great to be able to look back and also to be looking forward to a time when we're going to be putting feet back on the moon again, which I really believe will happen in the next couple of years. Okay. Well, I'm going to start with a story. So a couple of friends and I, colleagues, friends, buddies, were sitting in the back of one of these Land Cruisers and bumping along on a dirt road in Morocco. This is about 2016, summer of 2016, and noticed that we had quite a bit of wind. We were thinking a lot about sand dunes and what wind can do to a landscape. And we were excitedly talking about this idea to send a rotorcraft lander, a drone, to Titan. We had this idea run up to NASA, and we were one of about 12 finalists, 12 submissions, not even finalists yet, 12 submissions to this idea to do whatever it is you would propose to NASA. In our case, we wanted to send a helicopter, a rotorcraft, to Titan. And we were talking about names. What should we call this instrument? What should we call that instrument? What instrument should we have? What should we put on there? You know, excitedly arguing, but in the back of our minds thinking, well, this is the first time we've run this up and it's not going to go because it always takes a couple of times to put it in. But still, there's just a buzz and excitement around us. And in the car at the time was the mission architect two of the deputy principal investigators, and then me, a science team member, and just excitedly chattering and talking and watching the wind blow and being out in the desert and being inspired by being out in this beautiful landscape. Well, so fast forward, we actually got the mission. To our surprise, we got the mission much earlier than anybody ever expected, but it was such a great idea and so brave and exciting. And every time I thought about it, I got chills. And we ended up winning. And it was 3 years later, it was June of 2019 that Dragonfly was selected. And so it is part of the New Frontiers program. It's a sort of medium class mission, and it is designed to go and study Titan, Saturn's moon, Titan. And I guess I can say, you know, some of this is luck and it's right place at the right time. And some of it is just that this was just really exciting to all the upper NASA mission managers, and to be able to say, hey, we can do this. We can go to this place and we can study it. So there must have been something really compelling about Titan that sent us there. And I'm going to try to help you understand that, first of all. So this is a picture from the Voyager spacecraft. And this was a lot of the reason to even propel the Voyagers out there. Is Titan was exciting, even from Earth, from ground-based telescopes. We could tell it had an atmosphere of nitrogen that's similar to Earth's, not only in composition, but also in pressure. Same pressure as Earth's at the surface. And then in addition to that, you see this orange haze. We can't even see the surface. That's because there's lots of organic molecules all throughout the atmosphere. And we don't necessarily mean made by life, but it's the same composition as materials that life would use. Later, we would see from the Cassini mission propane, benzene, acetylene, all kinds of things in the upper atmosphere of Titan. And so plenty of materials there that maybe could be used by life. What is sitting on the surface of this body? What is it like? And it captured everybody's imagination, just this really tantalizing glimpse with Voyager before it headed off into the outer reaches of and beyond of the solar system. And just to kind of help you place Titan in the solar system, it's a little bit bigger than Mercury. Some of these objects out there in the outer solar system are really planet-like, and we almost don't really categorize them and stick them over in this moon category, but it's like a planet. I mean, in many ways, if I think of our own moon as a planetary body in terms of all the things it can tell us, the diversity of landscapes and of history, and Titan is no different. It's got a day that's about 16 Earth days as it revolves around Saturn, keeping one face pointed towards Saturn at all times. It's got a year that's similar to Saturn's year, so 30 Earth years. And, oh, actually, that's not, yeah, that's right. And then a gravity that's similar to the moon's. So despite the fact that it's larger, the gravity is like our Earth's moon, and that's just because it's got lower density materials inside. And I'll talk about that in just a minute. And as we said before, this atmospheric pressure is about 1.5 times that of Earth. So what's really fun to think about is if you could explore as a person on Titan, you wouldn't need a pressure suit. That's kind of a big deal. Pressure suits are really rough to design and to maintain and to operate in. You don't need that. All you need is a very warm winter coat and nothing exposed at all, because it's really cold. It's 90 Kelvin at the surface, and at that location, water is frozen solid as a rock into bedrock. But also about this atmosphere, the density of the atmosphere is about 4 times greater than Earth's. And just as a spoiler, that's really good for flight. It makes it very easy to fly, unlike Mars, where it's actually really difficult to fly. And yet we still managed to put a little helicopter on the surface a couple of years ago. As we said, it's larger than the moon. It actually has about 50-50 water, ice to rock and metal. So deep down in the interior is a core of rock and metal, just like an Earth would be. And on top of that is a shell of liquid water. Well, a shell of water, some part of it liquid sitting in there. And so that really operates as the crust. That's what's exposed at the surface. We don't see silicates or metals anywhere on the surface at all. Also, what's really cool about the location of Titan in the solar system is that methane can exist as a gas, a solid, or a liquid. So methane operates much as water does at Earth. And that's pretty neat because we've got a methane hydrologic cycle operating in this nitrogen-rich atmosphere at Titan. And suddenly that's a very Earth-like environment. It's something we're familiar with. It's something that is active and progressing and moving, but just with different materials at a different temperature and yet we end up with really similar processes and landscapes as we have on the Earth. And then, as we said before, there's lots of organics present, perfect ingredients for the chemistry of life. And then the other thing that's interesting about Titan and that propelled it forward in this list of potential targets for the New Frontiers program. If I said New Horizons, I meant New Frontiers. I always get that confused because New Horizons was the mission that went to Pluto under the New Frontiers program, but it's the New Frontiers NASA mission model that is sending us out with Dragonfly. But what enabled us to propose during this last call is that Titan is actually an ocean world. And that just means there is liquid water somewhere in this body. Earth is an ocean world. It's sort of the type example of ocean world. And we're applying a lot of those principles to other bodies in the solar system, like Europa, like Enceladus, and other objects that we think have a liquid water ocean underneath an icy crust. And really the outcome of an ocean is simply the fact that you've got ice. And if you bring it up to pressure and bring the temperature up as you go down into the interior, you're going to melt that ice. And so just about every object that has a water ice lithosphere has got liquid water in there somewhere and is an ocean world. And why is that exciting? Well, I mean, as far as we've understood, life thrives where there's liquid water. And so we want to look out there in the solar system wherever there is liquid water present and just see if it started somewhere else. We don't know that. We've only seen life present on the Earth. We haven't seen it on other objects yet. And yet, I mean, are we the only ones? Can we imagine that Earth is the only place that this could have happened? We look out there in the universe and see these trillions of other objects where life could have started. And so it's likely to have happened, right? Could it have also happened elsewhere in our solar system? And if we can find it, especially somewhere as far away as Titan, where we couldn't have transferred it there from Earth, Jupiter would get in the way of that, then we can start to imagine maybe life is common. And that would be a really profound thing for us to figure out. Okay, just a little bit more about this chemistry that's happening on Titan. What happens is that methane is broken up by photochemistry in the upper atmosphere, break up the carbon and hydrogen, and then recombine that into long chain organics. And some of those grow very big. You know, as you know about organics, you just keep adding on carbon and hydrogen, and you can get some really big molecules. And then those things gently snow down to the surface of Titan. And what happens to it from there? I mean, does it clump together? Does it become solidified by the liquid methane kind of helping, like making a sedimentary rock, like what happens on the Earth? Does that bedrock then get eroded by more methane rain and rivers? That's what I kind of think. And then you can create however many particle sizes you need for whatever geologic processes are going to happen there. And so that's really exciting because all of that's happening on the surface. These things could be happening also on other ocean worlds, but we think most likely they're happening on a seafloor or somewhere down below the surface. Although we should keep our minds open to the option that there are enough organics sitting on the surfaces of those bodies that things could happen there as well. But we know it's happening, at least this chemistry is happening on Titan. And so that makes Titan a singular destination for understanding the chemical processes on our own planet that supported the development of life. Okay, so we don't know how life came to form on Earth. Titan is like the early Earth. I'll try to show you that that's hopefully the case, and may hold the key for understanding our origins. Okay, so we thought this was important enough that we sent a whole spacecraft back to Saturn, and it was not only just to study Titan, but Titan was a really big part in that puzzle. Cassini was sent to Saturn to look at the Saturn system, to examine Saturn and its ring system and its complex moons, and a whole probe was brought to go down into the atmosphere of Titan and land on its surface. And it was prepared to do whatever it needed to. It could have splashed down into lakes or seas of methane, as we suspected would exist there based on how much methane there was in the atmosphere. It was saturated in methane, meaning there must be a lot of it on the surface, or it could have landed on a solid surface. And so there it went in 2004, down onto the surface of Titan. And as it went down, it took these beautiful images of the surface of channels, really mature and progressed channels, things that had been carved over time that might even still be filled. You see how they're kind of dark in color? Maybe they're filled right now with liquids at these regions, or filled with dust and other kinds of things that could sit in the bottom of the channels to be dark. And these are much more mature than any channels we've seen on Mars, I should indicate. Mars did have running water, probably rainfall, but this happened very early in its history and briefly. And it looks like on Titan, this is ongoing and also has happened for a long period of time. So these pictures are so exciting. And notice we didn't splash down, we landed on a solid surface around these rounded cobbles. And geologists always get excited about this. Oh, rounded cobbles, that means water, fluid flowed across this landscape and rounded, knocked off the edges to make these cobbles round. These cobbles, again, can't be made of silicates like we're used to on the Earth. They have to be made of either water ice or organics. Organic cobble, like what in the world does that mean? Is it a big giant plastic cobble? Yeah, maybe that's a good analog, a big plastic cobble, because that's what organics are made of. These materials on Titan are wide open. We don't really know exactly what they are because you can have a range of properties with organics: sticky, not sticky, hard, not hard. We think fairly low in density. We can kind of get at that at least. So that's exciting already. And this is all from the Huygens probe. After that, we continued to explore Titan with the Cassini orbiter. And so we'd fly by Titan and then go back and fly past Saturn, fly by a different moon. And we did that for 13 years at the Saturn system. The mission ended by plunging itself into Saturn's atmosphere in 2017. And this end of life was decided mainly because of Enceladus, a little bit because of Titan too, but mainly because all of a sudden we saw these geysers of water gushing out into space from Enceladus, a tiny little moon that should have been cold and dead, and yet had enough internal heat, either from tidal energy or radioactive decay or something similar, that this liquid water ocean was heated to the point of ejecting itself out into space. And so it'd be fairly easy to go and contaminate that with a spacecraft straying a little bit too close to the body and impacting. We didn't really purify Cassini because it wasn't supposed to go and contact any of these objects. And so to avoid that, it was sent into a fiery and dramatic death. And it was kind of a good closure. Like I know a lot of times missions will go on and the team will sort of disappear, a little bit like Voyager. Voyager is still going, and the team has largely been replaced. Just the time scale is so long. And so this allowed us to get together and, cry on each other's shoulders and be sad that the mission ended, and then continue to work. And we have been continuing to work on the data ever since then. Here's some of the data from Titan. So remember before, we can't see in the visible through the atmosphere because it's too hazy, but we can look through spectral windows that allow us to see down to the surface. And this instrument, the Cassini Visual and Infrared Mapping Spectrometer, has provided beautiful images of the surface. These are falsely colored, but they show you, notice these big orange patches at the equator. This is regions of sand, collections of sand all across the equatorial regions. This was kind of a big surprise. I mean, we thought we'd find these lakes and seas of methane, but instead we find deserts all across the equatorial region. And then you also see some kind of brighter patches, purplish and bluish, and those regions are continents. The biggest one in the upper right is called Xanadu, and it is a kind of water ice rich and probably organic bedrock rich continent and continental landmass. Other regions where you see purple might be regions where there's a little bit more water ice bedrock exposed. And you see some round features here too. Those are impact craters, most likely. And we have a few of them, and scattered across, we think maybe about 70 or so. That's a few fewer than we have on the Earth confirmed. Could the liquid on Titan's surface be methane? Yes. We think that any of the liquid that is on Titan's surface is going to be methane. And so, so that is something that we are pretty sure of. But in the early days, we only saw these desert regions and thought, okay, well, I don't know where all these lakes and seas are. Here's another image, a slightly different instrument. This is the Imaging Science Subsystem, kind of closer to visible camera, the same camera that took all the beautiful pictures of Saturn and the rings and the moons without atmospheres. And again, through different spectral windows, we could see these dark versus light patches. So not only are there dunes present at the equator, but they're dark in color, sort of like the dunes of Mars, although Mars's dunes are dark because they're made of basalt, and we know that's not true on Titan. So, okay, well, I guess they can't be made of water ice. That should be bright in color. That leaves us with the option of them being made of organics, which is really similar in composition to what the previous image showed. Those orange patches are rich in organics. Okay, that's a puzzle. Notice this other dark patch up at the polar region right here. And this has kind of more abrupt boundaries to it, abrupt margins. These are the lakes and seas that we were looking for. It turns out they were up at the polar regions. We didn't see them until the later stages of the mission where we did polar orbits a couple of years in. So that was kind of exciting. We also got some images, a little bit higher resolution of the surface from radar, synthetic aperture radar images that can peer through that atmosphere. It doesn't even care about the atmosphere at all, can see down to the surface and send a signal and receive it back. And so when we see bright areas, they are rough to radar, rough on the surface at that wavelength, about 2 centimeters. The dark patches are smooth to radar at that wavelength. And that tells us a little bit more about the materials. Notice this big dark patch in the upper left is still dark to radar. And that's because any liquids are very smooth to radar. The signal comes in and bounces off that flat surface and then continues off in the other direction and never returns to the instrument. And so any liquids in radar are always smooth. And that's another good confirmation that this is filled with liquid. Okay, so here's a map view again of that near infrared version of the images. We saw impact craters all across the surface. This is in the radar, these little insets. So here's a little impact crater, kind of eroded. So not only do the impacts form, but then they're eroded over time by the methane rainfall. So that's kind of exciting. And then the other thing we see are channels. So here's again this repeated channel system that we see from Huygens. And we also saw some of these channels from orbit. So here's a radar image of a bunch of channels on the right side. You see them flowing into this bright patch that we think is actually kind of a dry lake bed now, because this is at the desert equatorial regions. And then do you see this big semi-round feature that's consuming the entire left side of the image? This is about a 300-kilometer diameter impact crater, the largest one that we've seen on Titan. Again, really heavily eroded. It reminds me of Earth craters that have been eroded and just left kind of ridges and mountains that are being degraded over time. Okay, and then we also saw these polar lakes and seas, and these are so beautiful. Look at this colorized radar image. It's really hard to imagine this is anything other than a lake or a sea, right? You can see channels flowing into the lake, and in fact, some of these very big ones, one of which is Vid Flumina, is this kind of Nile river-like feature that we found and decided this has got to be filled right now with liquid. And I think that's what made it so exciting. That means there's methane raining onto the surface of Titan, flowing into these channels and then flowing into the lakes and seas. The only other body in the solar system like that is Earth. And so there's a real companionship between Titan and Earth in terms of the kinds of processes happening in both those places. And also what I like about these lakes and seas is that there's evidence of both filling and draining of the lake over time. So out here by the edges, to me, it kind of looks like these used to be a little more full than they are, and they're kind of starting to drain out into the lake. But when you look over at the bottom edge here, the bottom right, those morphologies almost look drowned, like they used to be lower, and now the liquid has come and filled them up. So to me, this is like right in between, where it's not the highest stage, it's not the lowest stage. And that tells me that both those occur over time, high stages and low stages. We also see mountains on Titan, tectonic structures, big, long, linear mountain ranges. And so that tells us there's internal heat and energy that's compressing this water ice crust together, buckling it up and forming mountain ranges. And that's kind of exciting. And because of this internal energy, we also think there's pretty good evidence for cryovolcanism. And it's weird that we would give it a different name. It's basically just melt the crust and bring that up to the surface. But because the crust is water ice, then we distinguish it from silicate volcanism by calling it cryovolcanism. So what is a cryovolcano? Well, it's liquid water flowing across the surface. And this feature is hard to imagine what else it would be, because there's a big crater in the middle. There are flows that come outward away from that. And so in some cases, somehow, this liquid water ocean can reach the surface and flow out as lava. That's, again, really exciting. You can bring liquid water in contact with all these organic materials, and that will lead to really interesting, we hope, chemistries that we could observe there. Okay, and then the most exciting thing for me is there are all of these equatorial fields of sand dunes. Okay, there are these long, dark lines. They're not quite like sand dunes we're used to in North and South America. On these two continents, we actually find dunes collected into valleys and basins that are kind of isolated. But this type of dune is really common all across the Sahara and Arabia, Southwest Africa. So it turns out to be the most abundant kind of dune on the Earth. This is an image of Titan's dunes. They're about like a half a mile wide, kilometer wide. They're spaced by a kilometer or two. They're very big features. They can be hundreds of kilometers long. And again, this is a radar picture. And so we're seeing things that are smooth to radar. But if you were to look with your eyes at them in the visible wavelengths, they would also be dark in color, made of organic sands. And we're puzzling over what that could mean. Organic sands, in my mind, I always say, okay, is it plastic? I actually have a stream table at BYU that uses a plastic sand. They ground up salsa dishes and put the different sizes and colors of salsa dishes based on their size out onto a table so that we could more quickly watch a system flow and evolve. If you use silicate, it's really heavy to have it on a table, but we can put this on a big aluminum table and then we can watch it change and move more quickly over time. The inertia is a little bit lower here, right? So is it like my plastic sands? They're small and round and hard. They're the right density, we think. But then I also think of the idea, yeah, but they need to be dark in color. So maybe they're more like grape nuts. I really like grape nuts. If you could round off the grape nuts and move those around, and that seems to be the key. They need to be small and round and hard. And so we can use the atmospheric density and pressure, the density of the grains that we think, the wind speeds we think are going to be there. And we come up with a size of sand that is probably about like sand size on Earth, only it's just made of these lighter particles. To me, that's the most exciting question to answer. What is the sand made of? How did it get there? It's like the accumulation of all the processes that have happened on Titan, all collected into this handful of sand. Whenever you walk on the beach, that's exactly what you can find. You pick up a handful of sand and say, okay, well, there's lots of quartz that's come from the Sierra Nevadas way up here, or in your case on the East Coast, that's come from the erosion of the Appalachian mountain range over time. And then maybe we find some other grains in there too, and that could be more recent kind of volcanoes that erupted and deposited their materials out there on the shore. And then you find really fine particles kind of inland from all the glacial activity that's happened up in the Northeast during the Ice Age. So sand just holds the key to all of those processes in one place. Okay, well, so I've said that they're like the linear dunes on Earth, but I didn't say how much like them they are. They're actually the exact same size and shape and behavior with obstacles and everything. That size and shape similarity, I think, occurs because the atmosphere is so similar to Earth's. We notice, we say, oh, this volcano is like volcanoes on the Earth, the ones we see on Mars, but it's much bigger. It's able to grow larger. Or this feature is like those on the Earth, but they're much smaller. But in the case of dunes, they're exactly the same size. So here are some in Libya. And in general, we think the winds blow from the left to the right in both these images. That's a real help to us because there are hundreds of thousands of sand dunes all across Titan, at least tens of thousands. I don't know if we've gotten to 100,000. And in each case, we think we can say the transport direction is down the dune long axis. So they can sort of act like an integrated weather vane or wind vane over time. And we can figure out the winds, at least that blow the sands, can blow mostly on Titan from the west to the east. So that's pretty neat. We were trying to make sure of this. Do the sands actually move down the dune long axis? And so we're trying to obtain information about the profile, the structure of the dune. And so here's a really long wavelength ground penetrating radar set over some dunes in Egypt. And we dragged that across with this truck right here. Here are some smaller versions of that ground penetrating radar that doesn't go quite as deep. But here you can see the interdune. There's a nice straight line right down the middle. And that shows that the substrate, which is made of petrified wood, it turns out 30 million year old petrified trees underlay all of these dunes. And we can see that pretty clearly with the ground penetrating radar. And then we see that the sands kind of go down the slope here. So that was our kind of initial stage of looking at dunes with this ground penetrating radar. And I'll come back to that in more detail later. So we've said we've got these key ingredients necessary for life. We've got energy from sunlight and photochemistry. Sitting on the surface, we have organic material. Then we also have two liquids, and we need to think about this as we're looking for evidence of life. There's liquid water that's occasional, either through impact craters or cryovolcanoes, but there's methane that's always there. And it turns out you can imagine a life that exists using methane rather than water as the liquid. It's a little bit different. It's not maybe quite as efficient as water is at doing the things that need to be done, but it's a possibility. And so on Titan's surface, we can study this prebiotic chemistry in this planetary environment that has Earth-like surface processes. And it would be also nice to look for evidence of life there, and we will try to do that as well. So here's Dragonfly. There's this idea that we had, well, what if we had a lander that's got this great aerial capability and could do in situ exploration? And it turns out that this environment at Titan means that we can have a pretty big spacecraft. So I'm holding just one blade of 16 of them all across the body, and it's as tall as I am. And so we can bring a lot of big instruments with us. This low gravity, this high density means that we can very easily pick up and fly as we need to. And so, so we were selected, I'm going to go back, hopefully this won't mess it up. We were selected for flight in June of 2019. And ever since then, I've been undergoing design. We're going through review this year with NASA, and that should wrap up by early next year. So here's exactly what we imagine will happen with Dragonfly. It's a single spacecraft. There's no orbiter. And so that means when it arrives at Titan, it goes down through the atmosphere, it detaches and just has to start up and fly. And it better work. And it's going to fly across the landscape. It will search out a good place to land. We've got to do this a little bit autonomously because the travel time for light is an hour and a half from Saturn. And so we're now in the region of autonomy. It will communicate direct to Earth with that antenna. It will perform science experiments there and then pick itself up again and fly to a new location. And this could be as much as like 30 kilometers away. So imagine taking all of that mobility and understanding of the landscape that we got from the rovers and then add to it that we can really pick up and go lots of different locations. And that makes Dragonfly a whole new way to explore a planetary surface. Okay, well, where do we plan to go? It turns out we need to go to the equator because we've got to communicate direct to Earth. So that eliminates some of the polar regions, and that might be too bad for the methane lakes and seas, but it makes me very happy because of all the sand dunes that are at the equator. And remember, the sand dunes are still rich in organics. And in fact, notice there's a little circle in the box, and that circle is an impact crater. And this is called SELC. So we can go to a place where there was liquid water dumped out onto the surface as an ejecta blanket or as melt inside the crater and see how that interacts with all those organics. And so we'll land just below the SELC crater and be able to test a whole variety of materials in that location. Well, we will also be able to pick up and fly. We'll use this leapfrog strategy. We can operate for as much as 3 years. I forgot to mention there's a radioactive power source on the back, and so that enables us to operate for 3 years. We can travel up to 180 kilometers so far, 25 to 30 unique sites. And in order to be the safest that we can in terms of landing, we'll first design the spacecraft to be really robust, but then also as we go to a new region that we've scouted before, we'll first overfly another region and then come back and land at that safe region, the region deemed to be safe. So the biggest nail biter is that very first landing, because we won't be able to determine in the back room that this is a safe location. There's going to have to be a little bit of autonomy. But beyond that, even during the landing, they will have scouted the new site and then come back and land at our first site. And so we use this leapfrog style to be able to safely go to new locations as we move forward. And so we have, and then on the bottom, you can see a whole bunch of different terrains. We call those alpha and beta and gamma, different kinds of terrains. There are the dunes, that's that alpha terrain. We have liquid water potentially that's in the ejecta blanket. There's the green terrains, the gamma, and then some other blobs of melt that exist as well. So we've got lots of different things that we can explore and characterize and lots of time to think about the areas where we want to go. And then, okay, so we said we were going to land in dunes. So we've got to be prepared to understand deserts and dune-like landscapes. So here's a trip that a few of us took a number of years ago to the Namib Sand Sea. This is in Southwest Africa. And you can see right here some big long dunes in red. They're dumping out into a river channel right here. And then we're standing in the space between the dunes, the interdunes, which is exactly what we're going to target with the Dragonfly spacecraft. And typically the interdunes are a little bit different from the dunes. They're kind of more of a soil, or they could be like an evaporite, like a salt flat. They could be a clay. Often they just don't contain sand. So you've got to go closer to the dune to get to the sand. But the interdune itself could also be really interesting. Here is an overhead view of the Namib Sand Sea. You can see these really long and straight and parallel dunes. And those really straight dunes mimic in a lot of ways the morphology of the dunes on Titan. So we wanted to get us a couple of different views, some dragonfly-like views, although at the time we didn't know about dragonfly when we were there. We just were thinking about how to explore these from the perspective of exploring Titan. So we got up in a little aircraft, and notice you can see each of those finger-like dunes stretching off into the horizon. And in this case, the dunes themselves are kind of wide. And so there is a lot of sand in this area. There's a big mountain protruding up, and notice it kind of diverts the dunes in their path. And then in this region, there are evaporite or salt flat or clay flat like interdune areas. And that's from liquids flowing in the subsurface and then evaporating away in certain regions of the dunes. This is really common in sand dunes. And so I kind of think the same things might be happening on Titan, where you have methane liquids flowing in between the dunes, and then they evaporate away and leave behind like a salt pan, but it would be organic salts. Okay, so it's really kind of hard to think about the same processes, but the different materials that are happening there. Here's what that looks like close up. It's a clay pan, a salt flat. You can even see liquids kind of flowing in from certain portions of that pan. And we'll be able to get that bird's eye view up overhead, and then we'll be able to get that ground level view to be able to integrate our understanding of the entire region. And that's really exciting. Something else we did on Titan is that we brought again with us this ground penetrating radar to see the layering in the subsurface. And this time we got some really good high resolution images. What we could see is that there's just sliding down the dune summit. Okay, that's the first level of what's going on. But deep down, we can see the scouring, the scooped-like shape. And this is from the winds carrying sand down the dune long axis, up and down the dune long axis, just as we expected. We feel like we found some good evidence that transport is along the dune long axis, and that tells us that winds generally blow along the axis. And so that's really helpful. It's like a climate or wind indicator that we can use for Titan, where we don't have these landed instruments yet. I have a couple questions in the chat. I might just answer those real quick. So could the liquid methane on Titan burn? Yes, it could if we had oxygen there, but luckily there's no free oxygen in the atmosphere. And so that's actually better for us in terms of exploration. It's maybe less exciting, but that's, it could if we introduce some oxygen there. And so then there's a question about comparing and contrasting the science of drone versus rover. Yeah, I mean, I think this is actually going to show that. We feel that the drone or the rover science was really good in terms of acting like a field geologist. You could go up to a rock surface, you could test it, then you could kind of walk further on and do some other testing. But because of having to be very careful with the rovers, that took a long time, much longer than it would take if you were actually there as a field geologist. And often they only made it 13, 20, 25 kilometers total in their 14 years of lifetime. And that's still significant because it's really interesting in terms of what we could learn. But what we'll be able to do with Dragonfly is a couple hundred kilometers of exploration potentially. And so that's just a whole new level of changing landscape and going to somewhere very new. And so, yeah, Ingenuity was really exciting and special. And I think the biggest lesson from Ingenuity is just that it can work. They had to spin up at something like 2,500 RPMs to be able to operate in the thin atmosphere of Mars. And they made it work over and over again. And it was successful. And they returned some great data, some neat overhead views of the landing site for Perseverance, which I think is really cool, like the chute and the back shell. And to be able to get the overhead view was valuable. So we want to make sure to take images all the way down to the surface, which is really good. Yeah, the rovers get covered in dust on Mars. We're working through those ideas. We don't think the problem is as big on Titan simply because there is rainfall that occurs. And so that's a big help, but we'll definitely consider some things. What would happen if dust can collect on the rover or on the lander, and how could we do it? We do have all those propellers, and we can actually create our own wind. And that's kind of interesting from rover science, because what if we get there and we want to see how the wind blows on the dunes, but there's no wind, and that could be a reality. We can make our own wind with the rotors, and that could also probably operate as a way to clean ourselves as well. Okay, awesome. So let's go on from here. Just a couple more sites to share with you, and then we'll get into the instruments. This is a beautiful image, a satellite image from Aster. And what it's showing are some mega dunes in the United Arab Emirates. And these are, again, a kilometer or two across. They're spaced by a couple kilometers. What's different here is that the interdunes are definitely evaporites or salt flats, and liquids constantly flow underneath the dunes here. We think that's what helps them grow into mega dunes. And so potentially that's what is happening on Titan as well. And notice that the dunes here, the interdunes here are a lighter color. They're evaporites. This is a border fence with Oman in the background. And boy, they get so big. This is a picture from the highway. They build roads over the top of these in the United Arab Emirates, and sometimes hotels. This is actually the same kind of dune, and could be the very dune that you'll recognize from Star Wars. And Jakku is nestled in between one of these two dunes. That's exactly where they filmed it. And so these are really impressive and fun to go and study. My students really love the opportunity to climb up on the top of them and bring instruments along and just take pictures up there too. But notice too the rich kind of structures that occur in the interdunes down here. And this is from biology. So even in this hyper-arid desert, biology extremophiles exist because of the really salty water that's here. So we want to be prepared to be able to recognize similar kinds of things on Titan if we see them. And then, of course, we want to get out and practice. I like to get out with my own little, I probably should name it Dragonfly, my own little drone, and look around at what overhead can tell us. And this looks very different from being on the ground. And so it's good to get those different perspectives and see the landscapes and the differences that occur there. Okay, so I just want to go into a little bit of detail about the instruments on board. And so here's one of them. This is called Draco. It's a drill, and it will operate through the legs. And the drill will actually go in and percussively act on the surface to be able to obtain some materials that it will draw up into the spacecraft, and then be able to put it into a mass spectrometer and study the composition of the surface there. So that's a really exciting instrument. And this one is pretty neat, and it's exciting, and it's moved forward. It's designed by Honeybee Robotics. Once it gets into a mass spectrometer, and this is a Goddard spaceflight mass spectrometer, it will be able to examine the full breadth of atomic weights of these particles. So we can look at really heavy molecules. What if they're heavy enough to be amino acids or lipids or other kinds of things like that? And that's really exciting. And we've got a couple of different modes of operation for the mass spectrometer. Then we also have a way to look into the near subsurface. So there's a gamma ray and neutron spectrometer. And so it's a remote sensing instrument, but it can look into the surface and just barely into the subsurface and be able to obtain a little bit of a spectrum of materials there as well. And so that's really valuable. And also it can tell us a little bit about the stratigraphy in that near subsurface. And then we've got a whole meteorology package. You can imagine, like, this is a mobile meteorology site. And so we'll look at temperature and pressure and relative humidity, just like you would in any kind of aircraft that you bring with you, right? There'll be like a little pitot tube, and it can monitor the atmospheric conditions, the methane reservoirs, and the transport, and even regolith properties. And then we will look at processes that might mix organics with either past liquid water or the subsurface ocean. And part of the way we're going to do that is with seismic activity. So we are actually going to bring a seismometer. It's provided by the Japanese Space Agency. And the details are still kind of being worked out, but think of the successes that happened with the InSight mission to Mars, and that we were actually able to determine the size of the core of Mars with their mass spectrometer. And ours is going to be much simpler because it's got to be able to be lowered and then retracted back up into the belly and transported with us to new sites. But differences in the wave patterns and the time, as you may remember with seismic wave patterns, is it's representative of the depth of the material. And so the difference in the patterns, we could simulate the difference between like a 46-kilometer thick ice shell and then 100 and I can't see that because of the other 124-kilometer thickness ice shell. And that's really interesting. How deep is that liquid water ocean? And if we could get at that with a seismometer, that would be great. And then my favorite are the cameras. I am a landscape geologist, and so for me, looking at things and seeing the landscape is very important. And we'll get panoramas, we'll get overhead views, we'll get from a landed perspective forward and downward, and even microscopic images of the surface, just like on Mars. And so here are pictures all from Mars's cameras, and especially this beautiful microscopic image of sands. I remember seeing this in a conference, and just my head just kind of flushed. I was like, oh, I'm so jealous of that picture of sand, and I want this picture of sand on Titan, and we should get it. So this is really exciting. I have a sand collection just because I love what it tells us so much. And here's a handful of glass sand from a beach in Hawaii, and it's really this kind of mystical, magical beach. But of course, I thought, okay, but if you go around the corner, you'll find a trash dump, and sure enough, that's what's there. And so the bottles break up, and then the glass gets transported over to this beach. So again, that sand tells you about the processes that happen. Okay, well, so we've done a little bit of testing. So here is a video from when engineers went out to the desert in California last year to bring, basically, I think it's a half-size model, maybe not even half. Okay, pretty exciting. I mean, I think what's really standing out is just the fact that this technology was ready. And I don't know how many of you own a drone, but it's really hard to, yeah, I mean, they're so fun, aren't they? And it's hard to lose or damage them. They take care of themselves, and they're pretty stable in all kinds of winds. And we're starting to learn that with these simulations, and getting very confident about the performance of this as we go forward. So I think we're in conclusion here. Titan really offers the next step to answer these fundamental questions. What makes a planet or a moon habitable? What is that prebiotic chemistry that occurred? What chemical processes led to the development of life? And has life developed elsewhere in our solar system? And we may be able, I didn't mention this before, but we might be able to see things like the chirality of molecules. This would be a really immediate answer to that question. Is something manipulating these big, heavy molecules, or do they just exist? And the chirality of things like lipids and other kinds of proteins, is that just random? And it's not random on the Earth, where life has interacted with it. So a few other simple tests and questions like that may be able to get us on that path to answering if there's actually life there. As we said before, the launch is in 2027 and the arrival is in 2034. It takes a long time to study these outer solar system bodies, but that's coming. It's coming rapidly, and we've got a lot to do before then anyway to get ready. So that is it for me. Thank you.
That was great. Thank you, Doc.
Fantastic.
Yeah. And we have more questions, of course, too. I'm going to start off with just one of mine. So if we're flying around on Titan, what are the chances that Dragonfly would actually recognize life? Unless it's spattered off the bugs spattered off the screen. I mean, what is the actual determination? Do you think that we would be able to detect life if it was small? If it was big, yeah, I get it. But if it's small.
Yeah, I mean, we do have to answer that question, like how small do we need to get to be able to see that? So, you know, things like single-celled life are going to be very hard. We don't have something that can see things that small. We've got the microscopic imager, but that's even sand grain size. That's big, right, for life. And so if there's something that big, okay, good, we'll be lucky. There was a little bit also on fluorescence with that microscopic imager. Maybe if the life is using fluorescence, that could help us to determine that. If there's organization to any sort of patterns that we see. Again, this idea of chirality, I really think would be a hard one to refute. But I feel like, as with any detection of life, and this will be true wherever we find it, you're going to have to do that over and over again, and you'll have to go back and you'll have to make sure and test that again, because at least that's what I would think so far. But I am also not an astrobiologist, and I don't know if I can come up with this real smoking gun kind of determination. But I think there are some things that would be very tantalizing and that could tip us in the direction of assuming that it could be there, based on what we have that we're bringing with us with Dragonfly.
And around the equator, it is sandy and deserty. So we're not going to be checking out any of the liquid. Are we going to be anywhere near where we're going to be able to see liquid moving and be able to, because that's where that seems like a pretty logical place to look for life too, is right along the edge.
Yeah, exactly. I think Chris McKay is an astrobiologist who said, hooray for beaches. You know, beaches are the place where we think that life is exposed the best. And so it would be great to be able to get up to the beaches of the lakes, but they're too far north for us to communicate with the Earth. So we don't think we're going to get there. However, I really think that there is good evidence for, I think that there is some evidence, and we'll continue to look for this, that liquids have been recently at the equatorial region. So there was a paper by Griffith and others that said, hey, there's some visual and infrared mapping spectrometer evidence of potentially liquids at the equatorial regions on sort of a broad pixel scale. And then, as I showed before in those UAE pictures, that's a hyper-arid desert. And yet, because of springs, there is liquid flowing underneath the dunes, and they emerge at those interdune locations. And then one other thing I forgot to mention is we have seen some near equatorial rainstorms with Cassini. And we saw a whole patch, brighten up and then kind of darken again. And the best explanation we have for that is a big rainfall event in that location that we need, because we have, we're near an impact crater. We can maybe even fly over to the region where the cryovolcano was. And then we've got the organics from the dunes. We've got potentially liquid methane, ponds or swampy areas, and we'd be able to go see those.
Franco, you had a question too, didn't you?
Yes, I'd like to know how it's going to navigate the Dragonfly, because does it have like recognition of the surface, or has it been mapped completely so that, for instance, it doesn't land on methane or liquid?
Right. Oh, that's a really good question. We don't have that middle range imaging that would be really good to have before we go. So the spacecraft's going to have to be pretty autonomous and pretty capable. There is going to be, there are all the images that we can obtain, and the spacecraft will use that to help, but there's also a landing, I think it's a radar, and I'm forgetting if that's exactly what it is, but definitely there's engineering cameras, engineering radar. I don't think it's LiDAR, I think it is actually radar, but that will be used to examine the area that it's landing in. The other thing that we can rely on is, in general, dune areas and the spaces between dunes are fairly flat. Also on Titan, any of the geology is water ice geology, which is overall much more subdued than silicate mountains. And so the highest mountains we have are just a couple kilometers. Most of the time, the average elevation is just 100 meters or so difference. And so the very gentle overall shape and topography of Titan is going to help us to be pretty safe.
Yeah, because it's going to be completely autonomous, right? Because
yes. So I mean, the images need to be able to say, like you said, ooh, is this a giant pool of methane? Maybe we don't want to land in it. And again, we can rely on that big survey that we can do, and then it comes back and lands, and we've got weeks, typically Earth weeks, right? Which is just a day of Titan, to be able to examine that data and say, okay, yeah, this is a safe area for us to land in.
Thank you.
Another question too, just more back to the organics or what Titan's atmosphere is actually composed of is Parima had asked, is it primarily nitrogen or methane in the atmosphere?
Mostly nitrogen. In fact, it's 95% nitrogen, so a higher percentage than for Earth. And the remainder is mostly methane.
All right.
Yep.
Stephen Schreier had asked too, what if you were to take seeds or something from Earth? Is there anything that you could plant? And I don't know why we would, but is there anything you could plant on Titan that would actually have a chance of growth? Is there anything that we could bring there from here to there that would have a chance of growing?
That's actually a really great question, because it's tied to this idea of planetary protection that we try to do as we're going to places where we could contaminate them, or vice versa if we're bringing samples back. And this can be a really kind of costly process. It can be difficult. It can cost as much as like $50 million to make sure that you can purify the spacecraft enough. It turns out we don't need to do that for Dragonfly. And the reason is the temperatures are so cold, we can't imagine anything on Earth operating at those temperatures. This 90 Kelvin is, minus 200 C or close to that, 200 C. And there's nowhere near those temperatures anywhere on the Earth. And so we just don't imagine a biology that we have that's going to work well there. We always get these lessons of like, well, you think that's true, and then you bring it somewhere and it can work. But so far, and people are trying to be very careful with this, so far it looks like anything we see or find or can do is just going to be totally different from what we have here on the Earth. And that's exciting.
Very. Yeah. I'm not seeing any questions. Is there anything else from the board? Because I have one last one. Anything else? Well, so you've spent a lot of time actually dreaming about going to all these different planets. You've done some of the most amazing trips in your mind, clearly, and then you actually made it happen. You went there. You did this. You sent stuff there to make these things happen. What do you envision as next? What are your next steps? Maybe, where else do you want to go? What else kind of things do you want to do?
Oh, that's a really great question. I kind of, as you mentioned before, I sort of grew up on Io, Jupiter's moon Io, which is so just exciting. It's the most volcanically active body in the solar system because of tidal massaging by Jupiter. And so I've kind of made a job of it to go out to landscapes on Earth that are like these places we find on other planets. They tend to be in really difficult, extreme locations, and lakes of lava are abundant on Io. And so I go find all the lakes of lava, and they might be in Ethiopia or in Hawaii or Vanuatu in the Southwest Pacific, and just try to study their thermal behavior so that we can compare that with what we see from telescopes and also orbiters at Io, and be prepared to understand that body a little better. And then same thing with the dunes of Titan. We're also studying wind-carved ridges that exist on Mars. And I would love to go and see these wind-carved ridges on Mars up close. Maybe they would make good habitats. And because you can sort of carve into them very easily, make a little, I'm back to Star Wars, make a little Star Wars-like home where you're safe from all the radiation and the cosmic rays and everything else that would happen on Mars. And there are lots of them all across the surface. And so for me, knowing all of these different landforms better is my most exciting, most immediate goal. Keep exploring the Earth and keep learning more about it. But I would love to get back to Io with the spacecraft. As you mentioned, we've run up a mission idea a couple of times, the Io Volcano Observer. We're going to get that ready again for another New Frontiers call, which they're working on right now, developing the actual call. And so we're excited about that one. There's a lot that Io can teach us about early Earth, for example, and tidal heating, which is really important for exoplanets and other exotic locations like that, where it's a source of heat we are not accustomed to. And what kind of environments can we get out of that? And then I've also been talking about a mission idea to Pluto. We've been to Pluto with the New Horizons spacecraft, but boy, if we could go back and orbit Pluto and study its big nitrogen glacier, and at that location, nitrogen atmosphere is collapsed onto the surface as a glacier and flows like toothpaste across the landscape. And so if we thought Titan was crazy with its cold temperatures. Pluto is just almost unfathomable. And I think it's got a lot of fun and interesting secrets that would teach us more about ocean worlds in the distant reaches of our solar system. So those two are really heavy on my mind. I would love for us to get out there and find an exoplanet. Can we go to Proxima Centauri and visit Proxima B and study those locations? Let's open our minds and think about the possibilities and try to get out to these distant locations. And if we start now, I think that we're setting the stage for what we want to do as a species from now on. So I hope we will do that.
What a great way to end it. Thank you, Dr. Radebaugh. That was incredible. And I cannot wait to see this thing launch. It's just, that's the problem with these deep space stuff, is it takes so long.
I know,
we all get so old as we watch this stuff, but when it happens, it's shocking. It's amazing. And it's just, it just gives you hope when everything else sort of seems like it's all going to hell in a handbasket. Something like this pops up and like, wow, the whole world gets behind it. It's amazing.
Yeah, please come to the launch. It'd be so exciting.
I'll take that as an invite. Yeah. Well, that's it, folks. We'll do this again next month. And we can't thank you enough for joining us, between Zoom and YouTube and everywhere else. And we appreciate it. And thank you so much for attending. And thank you, Doctor, for spending some time with us today. So we'll see you again next month. Bye, everybody.
Thank you.
Thank you. Good night.
Bye.